Unmute.
Selamat malam Bapak Ibu.
Selamat malam Pak Adit.
Ya, Bu Tri. Mohon maaf sudah menunggu ya, karena kita masih menunggu pembicara. Ini belum satupun pembicara kayaknya belum online ya. Mohon maaf karena perbedaan waktu 12 jam dengan para pembicara di benua Amerika, jadi saya mohon maaf. Halo, mohon maaf Bapak Ibu, kita mungkin bisa mulai dari Pak Cayo dari Unipol Meksiko. Halo, Mr. Cayo Tavares. Halo, Mr. Cayo. Do you hear me? Mr. Cayo, please turn on your mic.
Hello,
Halo.
Caio.
Hello, Mr. Cayo. Can you turn
Yes,
on your video, please?
yes, sure. Just a minute. Can you hear? Can you see me?
So, hello, Mr. Cayo.
Hello,
How are you?
I'm fine, and you?
I'm fine. Sorry for this situation. We are waiting the two other speakers, but unfortunately they have problem with maybe with the connection.
Okay.
Do you mind if you start the first presentation tonight?
No, yes, no problem. I can start.
Okay.
Yeah, I was surprised because I say, well, they're showing my presentation. It looks it's early, like
Yeah.
1 hour later.
I'm sorry.
No, no worry.
So after your presentation, I hope Mrs. Kiska will join with us and also Mr. Agus Sasmito. So
Okay. Thanks
first
so much by the invitation.
I will read the biography of Mr. Chayo Fazioli Tavares. He graduated from metallurgical engineering at FEI University in 1997. Can you explain us what is FEI University?
Yes, well, I'm in Brasilia, and this is a university in Brazil. It's called it's a FEI, that is a university of industrial engineering.
Okay. So after graduate, he worked at Institute of Energetic and Nuclear Research, or IPEN, in powder metallurgy.
Yes.
And from, I think, from 1998, he worked with investment casting industry and have experience with superalloys, heat treatment, and machining process. In 2007, he became an engineering manager. It's at Unipol or at the other company?
In another company is was in Aço Técnica in Brazil, as an investment casting company in Brazil.
Okay. In 2008, he completed his master science degree at Sao Paulo University, USP, Brazil. And the title of the thesis is the microstructure to predict the microstructure of austenitic steel casting. In 2013, he moved to cast iron foundry as a project manager, and in 2015 he joined with Unipol as technical manager at Mexico plant.
Yes.
So you want to share your presentation or?
Yes, I can share my presentation. Yes, as I mentioned, I have almost 25 years experience in castings, and what I'm going to present today was my thesis of the master that I did in 2008. It's to predict the delta Ferrite in austenitic stainless steels. Okay, I'll start to share the presentation. Can you see my screen?
Yes, it's okay. It's fine.
Okay, can start.
So, Mr. Chayo, you have more or less 45 minutes for the presentation, and for the question and answer is 15 minutes.
Okay. All right. Let's start the presentation.
Yes.
Well, the stainless steels, they have several applications, no? Because they have a good properties, a good combination of properties, no? As especially corrosions, resistance, toughness, weldability, and mechanical strength at low and high temperatures. But the properties of the stainless steel are most of the time related to the microstructure, especially the amount of the delta Ferrite in the microstructure. If you look here in this, if you see here in this picture, no, you see those dark. This is a typical microstructure of austenitic stainless steel, no? And what you see in the bottom is the austenite, and those darker areas are the delta Ferrite. You know? And usually, this small amount of the delta Ferrite is very helpful to reduce the hot tear susceptibility. In case of when you do welding on austenitic stainless steel, if the austenitic stainless steel is 100% austenitic, you may have hot tears, or also during the casting process may have hot tears. You know? And also this delta Ferrite increase the tensile strength and can be beneficial to avoid stress corrosion. However, the ductility is a little bit decreased and may precipitate sigma phase when exposed at elevated temperatures. No? And so we need to be very careful about the amount of delta Ferrite that you have on the stainless steel, according with the application that we use. Here's some examples of what the effect of this delta Ferrite. So in this graph was created by Schaeffler. You see here the amount of delta Ferrite. You see when we increase the amount of delta Ferrite, the strength increase of the stainless steel. And this other graph is a correlation between the chromium equivalent and nickel equivalent that you see later. No? So this relation basically will define the amount of delta Ferrite. No? And we see here when we have a low relation of the chromium and nickel equivalent, you have a high susceptibility to cracks on the stainless steel. And then after a certain amount, you don't have any more this issue. So basically, the stainless steels, they solidify in 4 different modes. We say mode A, that is here. When the stainless steel solidify in this way, you have a full austenite microstructure. In this mode B, you have austenite and ferrite microstructure. Most of the is austenite, but you have also ferrite. That is this mode. And on mode C, you have more ferrite than austenite. And mode D, you have 100% ferrite. So defined this way. And this solidification is basically driven by the chemical composition of the alloy and the cooling rate during the solidification. You see here in this picture, when you have the solidification by A mode, you see the dendrites are all austenite. When you have the mode B, you have austenite, and then start to have ferrite between the arms of the austenite. And then in mode C, the solidification starts with ferrite, that are those black arms. And then the austenite is formed in the interface of the liquid ferrite. This picture is the same, but you have more amount of ferrite. In these situations, like the mode D, we have only ferrite on the microstructure. So the phase diagrams are very important for the austenitic stainless steel, to predict the kind of microstructure that you have. But unfortunately, most of the composition that we have in the market have more than 5 components on the composition. And it's very difficult to find phase diagrams for stainless steel. Basically, what we find in the market are empirical methods, maps that indicate the amounts of the microstructure. This is an example of empirical method where we have here the chromium equivalent and nickel equivalent. So the author, what he did, he take other elements like the chromium, manganese, and convert a nickel equivalent. Here I have molybdenum, silicon, columbium, niobium. That is converted in chromium equivalent. So in this way, we have like a 2D phase diagram that is easier to predict the microstructure. This formula here to calculate the nickel equivalent and chromium equivalent, there are a lot of expressions in the literature to calculate the nickel and chromium equivalent. I cited here like 9 different authors that create different expressions to calculate the nickel equivalent and chromium equivalent. So they use different coefficients for each element. You see there is a big range of formulas and by different authors in different years. Many of them are applied to weldings, and but some ones are applied to castings. So what we did here in this work, the intention of this work was to evaluate the effect of the chemical composition of the alloys and the cooling rate of the alloys and on the microstructure of the stainless steels. So we made stainless steel shards in approximately 100 kilos, and we checked the chemical composition of 16 elements. So in total, we made also 16 different heats, and this stainless steel was melted on a temperature that you see another temperature and was poured in a ceramic mold that was made by investment casting. To evaluate the effect of the cooling rate, we used a test sample with different thickness, and we placed a thermocouple inside to check the cooling rate. And after cast, we combine the results that we got in the casting simulation with solid cast and the results that we got here in those samples, and we got those cooling rates of 0.78, 75, 1.5, and 2.7 kelvins per second in different steps of this sample. And the delta Fahrenheit was determined by using a Fisher ferritoscope in several locations of these specimens. And also we looked in the microscope the delta Fahrenheit distribution. So this is the test specimen that we used in this work. It's a later test specimen with 3 different thickness, started with 10 millimeter, 20 millimeter, 30 millimeters, and 40 millimeters. The gating area was, this is the feeder of this test specimen. And the metals go here inside and solidify this way. And the intention of this testing specimen with different thickness was to evaluate different cooling rates. Because here, when you have 10 millimeters, cool very fast, and on 40 millimeter, take longer to cool for the solidification. And then the intention was to evaluate what this the effect of this thickness difference on the solidification. We measure the ferrite with this equipment. It's called the ferritoscope. The intention was to evaluate. And how it works. This ferritoscope has a probe, and by induction, create you have here a magnetic field that is created here, and according with the ferrite that you have here, that is the ferrite is magnetic, create a different signal, and you read it here in voltage. So according with the voltage, you get a different percentage of ferrite. And those are the chemical composition of the alloys that we cast. See, 16 different heats in different stainless steels. And here all the composition of this alloy that we got in the spectrometer. And those was the pouring temperature of those samples. So these maps shows how we measure the ferrite on this sample. The sample was sectioned in the middle, the longitudinal direction, and we divided the samples in small squares, and we measured the ferrite in each one of those points. So we came here in each one of those points with the probe, and we measured the ferrite content. So here is the distribution of the ferrite in different thickness of the sample. So, and those are the averages of ferrite that we got. Here the example of the microstructure in one of the heats. So we have here the section with 10 millimeters, with different magnification, with 20 millimeters with different magnification, 30, and 40 millimeters with different magnification. We observed a little bit of difference on this, this concentration of the ferrite in the microstructure. And this was the heat number 8. So you can hear this table. We have some heats, those three first heats, we didn't have any ferrite content, was 0, no sample. And the last one also. And those other ones, we got different ferrites. We see here on the average of heat thickness, here on the average with 10 millimeter, with 20, 30, and 40, and the standard deviation that was observed in each thickness. So, as I made several measurements in each thickness, so we got the average and standard deviation. So then it was created a graphic, to evaluate the variation of delta ferrite against the thickness. So we have here those 4 thickness, 10, 20, 30, and 40 millimeter, and the amount of delta ferrite that we observe in each one. In some samples, we saw an increase of delta ferrite according with the thickness, but in some ones we didn't see too much variation. So it's the effect of delta ferrite in the thickness is not very marked or pronunciated. So here the analysis of the practical methods. So after getting those results of now in these practical samples, those 16 samples, no? What is the intention? Always compare the results that we got on this on the far right with those formulas that I showed in the beginning to compare the efficiency of each formula, to see the ones that the formula that is closer to the results that we got. So first of all, we need to calculate the chromium equivalent and nickel equivalent. Use the proposed expressions, no? Are the expression that I showed here in the beginning. Come back a little bit. What? Using those formulas. So we tested all those formulas in this study against the results that we got in the samples. No? And then when you get those values, so we need to go to diagrams like that to get to evaluate the amount of fluorite that you have on this microstructure. But unfortunately, there are some authors that they propose only the formulas to calculate the chromium nickel equivalent. However, they don't give us any isoferrite diagram. So when we use those formulas, we need to use the isoferrite diagram from another author. And then here we see here on the picture 11, the calculations of this delta ferrite. You know? So what we did here, no? Basically on this picture one, we use the chromium nickel equivalent and isoferrite proposed by Scheffler. It's one of these authors. DeLong, Seward, and Schoeffel. In this one, we plot the results using the isoferrite line is proposed by Scheffler, DeLong, and Seward, and using the chromium nickel equivalent proposed by Scheffler, and Hammer and Swift. So here in each one, we use the different maps here that we use Scheffler, DeLong, and Seward, and we test those formulas to evaluate the one that is closer to what is predicted here. So in order to interpret the results, no, so we use some statistical parameters for calculating each group of alloy to understand the differences to understand better the difference between each formula. No? So we calculate the relative error, the error, the standard deviation, and here the CI is a critical interval. And here was the errors that we got, the standard relative errors, error, standard deviation, critical interval of each of these studies that we did. And those are the graphics that observed there. And so our conclusions here was, if we made the different step thickeners later in this work, to show the cooling rate in amount of ferrite on the microstructure. So we see that those samples have different cooling rates, but however have a weak effect on the amount of ferrite. And we see that in 50% of the specimens with ferrite in the microstructures, the hypothesis indicates that increasing cooling rate decreases the amount of ferrite. It is in agreement with some results presented by King et al. And Pereira and Beach. The calculation of ferrite fractions using practical methods proposed by Seward give us the lowest relative error among the 19 methods examined in this work. So this was the best formula that we got that represents that's closer to the results that we got in ferrite content in our samples. And also another formula that gives us low relative errors was a combination of nickel equivalent proposed by Hu with the isoferrite suggested by Chapter, and also nickel and chrome equivalent proposed by Hammer and Svensson, with isoferrite lines suggested by Seward. So those three examples or practical methods give us a good combination of low systematic random errors, and but Seward was constructed for stainless steel welds, but even that this diagram was constructed for welds, worked well with the castings. So, was very good to predict the ferrite in castings. And are more accurate than the calculators by Schoeffer that was specially developed for castings. And that is current on this STM standard to predict the ferrite fractions of the stainless steel. Here the reference. I think I made it quicker than.
Okay. Thank you very much, Mr. Chayo, for the presentation. We have one question from Mrs. Frieda.
Okay.
Her question is how to control your experiment? Is it based on time or performance?
So basically was this experiment was controlled with the cooling rate of the samples. No? We have probes on this cooling and these samples, and with these probes, we measure the cooling rate, temperature, the curve during the solidification, and also the temperatures and chemical composition were controlled during the experiments. Not sure if I answered your question.
To my understand, you control the cooling rate by thickness of the mold.
Yes, and there is a thermocouple inside of each thickness, no? And we took readings of the temperatures along the time, and we made curves, cooling rate curves with the time.
And what is the medium for the cooling? Is it air or you use liquid?
We use the calmer air, environmental temperature, 20 degrees Celsius.
Okay. The next question, still from Mrs. Frieda. In manufacturing line industrial engineering, we are concerned on the trade-off point to get efficiency. So, in your experiments, do you get this trade-off point from your experiment? I mean, maybe the optimum result.
I didn't get very well. The question is
maybe she asked about the optimum result of your experiment. What is the best thickness or the best cooling rate to get optimum of the delta ferrite?
In fact, once we didn't observe a very pronunciated effect on the thickness, no? I don't know if you can see my screen here. I'm checking this graphic, okay. So what we were expecting was a difference like that, you know, increasing in thickness to get more delta ferrite. But in some situations was almost flat, you know, didn't have too much effect on this this formation of the delta ferrite. You know. Seems that is it's a combination of the chemical composition and this geometry of the castings. And sometimes it's more pronunciated, but sometimes it's not so pronunciated.
Okay. Do we still have any question? So maybe in the metallurgical course, usually we mostly discuss about the steel, not the stainless steel. Can you explain to the participant what is the difference between the delta ferrite and alpha ferrite?
Okay. Basically, in the steels, no, and the most common steels are basically formed of iron, carbon, silicon, and those steels are magnetic, you know. And in the case of the stainless steel, you have addition of some elements like chromium, nickel, and the intention of those elements is to increase the resistance for corrosion in the case of the carbon steels, the materials is can say cubic of the center of the body, you know, and on the stainless steel you have cubic with faces centered, and they are not usually not magnetic as the carbon steels, no. Just a little bit that this is what I showed here. That is this delta ferrite, and I think this is the main difference between one and other.
Okay, so that's why you calculate the ferrite, the delta ferrite by using I don't remember the name of the equipment. It's
Ferroscopic.
Because
Yes,
the
yes.
austenite is non-magnetic, as I remember.
Yes,
so,
that's correct.
And the delta ferrite is magnetic. So you use the, I think it's a eddy current method.
Yes, yes. Like eddy current to distinguish the amount of the magnetic portion that you have inside the microcircuit.
Okay. So we are still waiting for the next question. So I will ask you again, Mr. Chayo.
Okay.
Even though I don't teach the course in steel, but I just curious about in your slide. It is written that the delta ferrite can reduce the hot tear susceptibility.
Yes.
Can you explain to us the how this delta ferrite reduce the hot tear susceptibility of the stainless steel? What is the mechanism?
Usually what happens, you know, the main issue when we have a stainless steel that is 100% austenitic, you know, there is zero ferrite in a microstructure. The experience that I have in casting is when you have zero ferrite in a microstructure, usually during the solidification, we have, it's very common to see hot tears. And also, when this kind of component is required welding, it's very common to happen this. No? And why this happen? Because look in this graph, you know, that tells about the susceptibility to have the hot tears. No? What has happened? There is phosphorus and sulfur in the composition. No? If the amount of those tramp elements is not very low, if you have just a little bit of those elements, you may have cracking. You know? And when you have the delta ferrite, and those elements are dissolved in the delta ferrite and minimize the susceptibility to get crackings or hot tears in elevated temperatures.
Yes, but what I miss from the what we call it physical metallurgy. Can you explain why, if there is a significant amount of delta ferrite, then the hot tear susceptibility of the stainless steel lowers?
Yeah, what's happening, the mechanism that happen is we have on the chemical composition trace of those elements, phosphorus and sulfur. And then during the solidification, it goes to the grain boundaries, and you lose resistance of this component, because you have those trace elements on the ground boundaries. That is the point that can generate crackings on the castings or weldings. So in the case of weldings, physically is that what happened? You have those trace elements, those trash on the grain boundaries, and you get a fragilization in these areas.
So you mean by presence of the delta ferrite, the element of the phosphor and sulfur, usually they precipitate on the grain boundary of the austenite. But
Yes.
if there is a significant amount of delta ferrite, this the precipitation can be avoided.
Can be avoided. And this is not a significant amount. We are talking about like 4%, between 4 and 8%.
Okay.
Not too much, but it's important to have some delta ferrite in this in stainless steels for some applications, to avoid these kind of issues. And when I made this work, this master, I was working in a company in Brazil that were doing parts for nuclear applications, for nuclear power generation, and those parts go inside this equipment. And this was very important to avoid cracks during the operation of those parts.
Okay. We have a question from Mr. Suherman, Mr. Chayo. How to predict the amount of delta ferrite on stainless steel with large amount of mangan?
Mono is molybdenum?
Mn, manganese.
Manganese, okay. You see here on the formulas, the amount of manganese is considered as nickel equivalent. So in fact, everything that is those elements that are represented as nickel equivalent are elements that are austenitized. They create austenite on the microstructure. And those chromium equivalent are elements that generate ferrite in the microstructure. This is that. So in the case of manganese, is just consider here, you have to input the amount of manganese on this calculation, and then you get the right prediction of the ferrite.
Okay. So the participants, do you have any question? So at your company, Unipol, the product is stainless steel, or there is any kind of steel that the company produce?
In fact, this company that I'm working now, Unipol, we work only with super alloys. So our main products are like this kind of products, blades for aerospace, or this is true, like this turbine wheels. This is our main product, are turbine wheels that go inside the turbocharger.
Okay.
Or for cars or trucks.
And
parts, the material is nickel-based alloy and cast in vacuum.
Oh, it's investment casting?
Yes, it's investment cast. You have a thickness like more than less than 1 millimeter, 0.5 millimeters of thickness, something like that.
Okay. So that's nice.
It's very difficult to do those casting.
Vacuum process is only in Mexico or?
No. In Unipol, we have 3 plants. No, we have one plant in China, one plant in India, and here in Mexico. No? The plant in China is for the Asia market. The plant in India is for the European market, and the plant here in Mexico is for the American market.
Okay. Okay. So, do we still have any question? Okay. So, if we don't have any question, in my opinion, it's a very good presentation, Mr. Chayo, because it's a compare between the experiment and also the I think the simulation.
Yes, the comparison of yes, the practical and those formulas that we find in the literature. We made a comparison between studies that we got in the literature with some practical experiments.
Okay. Okay. So I think we don't have any question. Sorry, we still have, because we still have time.
Okay.
It's also from Mr. Suherman. Whether the size of delta ferrite on stainless affect corrosion resistance and mechanical properties? Does the size of delta ferrite affect the corrosion resistant and mechanical properties of the stainless steel?
Yes, the mechanical properties, the tendency is to increase the mechanical properties, but reduce a little bit the resistance for corrosion. So we need to be careful when we play with delta ferrite in stainless steel, to don't compromise also the corrosion resistance of the alloy.
And usually, what is the typical of the corrosions? It's a pitting corrosion or?
Usually it's pitting corrosion. I'm not a very expert in this subject, but I say that it's pitting corrosion.
Okay. So we don't have any question, Mr. Chayo. Thank you very much for your great presentation. We thank you for your kindness to join with us tonight. Maybe in Mexico it's in the morning, I think.
Yes, it's almost 7 in the morning.
So it's we have I don't know, maybe 11 or 12 hours of different time difference.
what you will know is Monday night, right? I'm starting the day. I'm starting Monday. You are in the future.
Yes. So thank you very much, Mr. Chayo.
Yes.
And
Yep.
I'm sorry for any inconvenient situation during
No problem.
during this online seminar.
No problem. And thank you also very much by the invitation. I really appreciate it. Be part of this group to present my work.
So I'm pretty sure that I will contact you next year to
Great.
tell us about what is the investment casting on the superalloys.
Yes, I can talk a little bit about that.
Okay.
We're very glad to talk.
Okay.
Thanks so much for the invitation.
Okay, so thank you very much, Mr. Chayo.
Thank you. Stop sharing.
Okay. So we have already Mrs. Giska Ramadita.
Excuse me, Mr.
Mohon
Moderator.
Pak Suherman
Agus here.
dan yang lainnya unmute, please unmute your mic.
Excuse me, Mr. Moderator. Agus here. Can I make the presentation first because I need to leave in about an hour?
Oh, so it's Professor Agus Pesasmito.
Yes.
So sorry, Mrs. Giska, if you don't mind, we allow the Professor Agus Sasmito to present his presentation first.
Yep, sure, no problem. Yeah, I'm looking forward to hearing Prof. Agus' presentation.
So we are glad to have Mr. Professor Agus Pesasmito from Department of Metallurgy Engineering at McGill University at Montreal. So I don't have to talk anymore. Please, Prof. Agus, the screen
do you see my screen, by the way?
Yeah, it's okay. It's fine.
Okay, good night, good evening, ladies and gentlemen in Indonesia.
Hello, what can I do for you?
Sorry, this is my phone. Excuse me. So before I start my presentation, just we'll have a quick background introducing myself. I'm originally Indonesian. I got my bachelor from UGM in 2005, and then I received my PhD in National University of Singapore in 2011, and then got some postdoctoral experience in Master Institute Abu Dhabi, the United Arab Emirates, and from 2014 I moved to McGill University in Montreal. I'll just talk a little bit. This is the outline of my presentation. It's quite long, but I'll just introduce one of my research that I'm doing now, which is basically microwaving the rocks. For those of you who are not familiar with McGill, McGill is not that well known in Indonesia, I would say. But in Canada, it is one of the best university in the country. We will celebrate 200 years anniversary next year. And we are, like, according to some of the world ranking, we are in a pretty good ranking worldwide. And especially in mining and mineral engineering, we are the first in Canada. We have about 41,000 total of students, with about 1/3 is the international student. And about quarter of the students are graduate students. We have the highest number of PhD students among Canadian universities, with about 12 Nobel Prize winners. And we have quite intensive research, with about 65% revenue of the universities are from research, not from tuition. I'm in Faculty of Engineering. We have 1, 2, 3, 4, 5, 6, 7, 8 departments of engineering, and I'm in the Mining and Materials Engineering department. which is the oldest mining and mineral engineering department in North America. Next year, we will celebrate our 150th anniversary. So in our department, we have 2 programs, which is the mining engineering and materials engineering with 22 professors and 3 groups of the research topic, which is mining, processing, and materials. I belong to the mining group, and this is the mining group at McGill. And this is my research group that currently I have 2 postdocs and 8 PhD students, 8 master students. This is just a little bit background on the activities and example of research topic in my group. We are doing a lot of simulations and experiment. We are equipped with high performance computing facilities under Compute Canada with more than 1,000 processors. We also have some experimental equipment like geothermal extraction, ground freezing, rock microwave system, and access to McGill characterization facilities. So this is some of the ongoing projects on my lab. It's quite diverse, from the freezing the ground to ventilate the mines, to microwaving the rocks, extracting the geothermal energy, solid liquid mixing, separation and reaction in mineral processing and mineral separations, energy storage, and so forth. What I'm gonna talk this evening is one of my research topic on rock microwave system. This project is in collaboration with Anglo Group, De Beers, Zenvic, Metso, ArcelorMittal, and Archex Titanium. Just to give you a little background story about the motivation why we do this project was that the future of mining, like the mining industry, just to give you an overview about mining industry in Canada, it's one of the biggest industry in the country, which basically contributes to about 20% of the Canadian export. And the mining industry has been around for about more than 100 years. And the advancement in the mining industry and research is very active here in the country. So the government, industry, and the academia, we have a vision of the mine of future, which mining will be all automated, continuous, everything will be remote. We will have pre-concentration and more effective mineral processing, more sustainable, reduced carbon footprint, and environmentally more friendly. So one of the challenges here in the mining industry is that for hard rock especially, is the mining method is usually it is drill and blast. So when we know where is the ore, we drill the ore, we blast it, and then we mark, and then we transport it, send it to the crusher, from crusher and then to the grinder, and the subsequent mineral processing. So hard rock, the challenge of the hard rock, if you notice that the energy requirement for crushing, grinding is huge because of the strength of the rock. And also it is impossible to mine the hard rock with the continuous mining machine. When we do a drill and blast, basically, it is a batch system. We need to drill, to blast, to mark, and the productivity of such techniques is pretty low. The future of the mine, in other hand, is to create a continuous mining system. So we are working with some of the manufacturer companies in order to develop technology to create a machine that is able to excavate the hard rock continuously. One of the challenges when we are designing mechanical cutter to excavate hard rock is that slow and low penetration rate, and the wear of the cutting disc is very high. This is example of the disc cutter that is used to cut hard rock of I think nickel ore, and you see here the wear of the cutting tool that is quite significant. So we have idea that instead of cutting the hard rock directly, why don't we reduce the strength of the rock by preconditioning the rock, and then we attack with the mechanical breakage. So we evaluate several technologies to evaluate the tool or ways to fragment the rock from the mechanical, thermal, fluid, sonic wave, chemical, electrical, and light, like laser. So our conclusion, this was done, the study was done in 2008, and the conclusion of the studies is that combination of electromagnetic induction, which is microwave, with the mechanical force, like tools, mechanical tools, is among the best in order to develop the continuous mining machine. So microwave has been selected, and we have been working on microwave since then. We evaluate how the microwave affect the rocks, how the microwave will create cracks in the grain boundaries, and then how we use microwave to precondition the rock before it is excavated using a continuous machine such as tunnel boring machine or a mechanical cutter. So we evaluate different failure mechanism when we microwave the rocks in the lab. There are basically two different modes of failure at different heating rate. When we irradiate the rocks with the low microwave irradiation, basically the rock heats slowly and expands slowly, which will typically result in diagonal cracks. While if we use high energy intensity of microwave, the cracks usually based on the tensile and sudden expansion, it often cause a spallation of the rocks. So this is example of the photograph when we microwave the rocks. Some of the rock surface become softened and sometimes it spalled. In our lab, we have different microwave facilities from 3 kilowatt, 15 kilowatt, and at the moment we are building 100 kilowatt of microwave for pilot demonstration in the field. So we did some tests to microwave the rocks with different intensity, different distance from the antenna, and different exposure time. We use different types of rocks like basalt. We have some sample from kimberlite from our industry partner, iron ore from our industry partner as well. And then we irradiate the rocks. We characterize the cracks using SEM. We measure the crack density, the length, the size. And we can see here after the rock is being microwaved, it creates micro cracks. We also quantified using the, you see here, the non-treated sample. Basically, there is almost no micro cracks occurring when we microwave the sample at 3 kilowatt and 60 seconds with different distance from the microwave antenna. We get different crack patterns. This is another example of the result. And when we, the result is summarized here, basically when we increase the power level of microwave, the crack density increases. And also when we increase the microwave duration, also it affects the crack development. We then did the mini CT scan to have a better three-dimensional images of the cracks. This is example of the non-treated sample and the treated sample of the core. After microwave, we can see inside the sample we find the cracks. This is, if you can see here, some of the cracks are generated inside the samples. And this is another example of the block of rocks that has been microwaved and spalled. The effect of the microwave, and then we measure it, the tensile strength of the rock. It is evident here that after microwaving the rock, the strength of the rock decreases. And when this is 0, it means that the sample completely broken. And in some cases, the rock melts because it heats too much. This is actually what we don't want to do, is to heat up the rocks and melt the rocks. Because in some of our sample, we got the kimberlite sample from diamond mines, and the company basically doesn't want to burn the diamond. So what we want to do is really to reduce the strength of the rock and then attack it with the mechanical cutter, and some of the micro crack still there in the rocks, which further will help on the crushing and grinding of the rock, so that the energy from mine to mill can be reduced significantly. Not only experiment, we also model this. This microwave rock system is quite challenging to model because it involves several physics, like the electromagnetic, which based on Maxwell theory. If we look into the mathematics of it, it is basically hyperbolic partial differential equation coupled with the heat transfer theory, which is basically parabolic equation, and then the mechanical or solid mechanics theory. And it has to be three-way coupling here, because when you microwave the rock gets heats up, and then the thermophysical and dielectric properties of the rock is also temperature dependent. When, for example, the permissivity of the rock at temperature 25 degrees Celsius will be different than the permissivity of rock at 200 degrees Celsius. So that's why it has to be fully coupled between electromagnetic and the thermal, and then the thermal will expand, create expansion of the grain boundaries, and it creates cracks. That cracks will also affect the heat transfer because of the release of the energy. It affects the heat transfer. So we model the three-way coupling of wave, thermal, and mechanical system of our rock microwave. This is a little bit theory of the governing equation, like the Maxwell equation, the heat transfer equation, and the solid mechanics equation. We measure the thermophysical and dielectric properties of the rocks. One of the challenges here is that some rocks are homogeneous, but most of the ores are heterogeneous, meaning that there are a lot of variabilities of the grain of the rocks, which make it very challenging. So we have two approaches here. The first one is a pore scale model. The second one is volume average model. The pore scale model basically is more accurate, but computationally it is much more expensive. So we try to bridge the gap by correlating a pore scale behavior with the volume average behavior in order to optimize the computational cost. This is example of the result of our simulation, how we can predict the electric and magnetic field within the rock, how does different rock characteristic, different microwave design affect the distribution of electric and magnetic wave, and it result in the different heating rate and heating pattern, and it is validated with our experimental measurement from the thermal camera. So this is we extensively validate our model, not only at one or two condition, but at various different condition, and we have been able to validate the model with the accuracy, a very good accuracy, with error within less than 5%. So this at the moment we are working on coupling it with the tool, so we already able to model and map the wave thermal and mechanical, and now we are working on coupling the model with mechanical tool so that we can use the model to design to assist on the design of the mechanical cutter. I also have two students that now are working on the effect of microwave on grinding and crushing of the ore. And we are looking into the possibility of using microwave to reduce the energy in grinding and also to improve the particle size distribution and recovery rate. And we also use a microwave for drying and dry processing of the minerals. I guess that's about it. It's quite fast. So if you have any question or discussion, feel free. I guess that's about it from me. Thank you.
Okay. Thank you very much, Prof. Agus P. Sasmito. So for the participant, because Prof. Agus is Indonesian, you can ask a question in Indonesian. So please. So we have one from Mrs. Frieda. Today, Freeport asked not to make a new smelter in Papua and just expand in Gresik. Is it more efficient to process the mineral outside Indonesia by doing exporting the ores?
Well, this is a very good question, and building smelter is here is the thing, like building smelter, we need to have there are a lot of factors, like for example smelter, we need very stable power requirement. So for example in Valley in Sulawesi, they have their own smelter, they own their own power hydropower to ensure that the power supply never cut off. The tricky part with the smelter is really in the power. When you lose a power supply, and then the whole process basically will be ruined. If we have enough power supply, like electricity, to supply the smelter plant, then I think it will be good for our country to have our own smelter. But also that is one aspect, power, and then the skill of the engineer. But I have no doubt on the skills of engineer in Indonesia. But I mean the technology for smelting is quite common as well, but it has to be imported, right? So in my opinion, if we have smelter in our country, it will have benefit to us, but we need to ensure that we have all the supporting facilities in order to run the smelter without any disruption.
Okay, also the main factor is the electrical power of the smelter.
Yeah, one of the big challenge, like in Papua, when the electrification ratio is very low and it is far from the source of the energy. If you want to build smelter, you need to ensure that you have very stable and constant electrical power.
Okay, but from the point of the mineral resources, what is your opinion about the readiness of the Indonesia to build a smelter?
I think from the technology point of view, I don't think we have a problem. We have a lot of experts in the metallurgy, and I think I'm not sure about the regulation right now. From the technology point of view, even though it is still important, but I think by having one, then people can learn more about the technology, and I really hope that the mining and steel industry in Indonesia be aware and have their own R&D department, so that we do not always rely on the overseas technology, and also the uh, collaboration between industry, university can be strengthened to develop the technology that can be applied in the country.
Okay, so we back to the topic, Prof. Agus. The technology by using this microwave, is it suitable for the mining on the surface or under the surface?
Well, this technology is developed both for surface and underground mines. Uh, for the surface, usually, maybe in Indonesia, most of the mines, maybe it's far from the residential area, but in Canada, many of the mines are very close to the residential area. And when we drill and blast in a mine that is close to a residential area, it creates a lot of pollution, noises. If we are using continuous excavation machine, at least we can avoid blasting. It is more environmentally friendly, and from the production rate point of view, it is much more efficient. Because of the drill and blast system, it is basically cyclic. It's a batch system, while machine, we can mine it continuously. And if you look at the production rate, for example, for using continuous excavation in soft rock, like in coal mine, for example, the longwall shear, the productivity can be up to 4,000 tons per hour, while typical drill and blast mine in underground, like if you get 4,000 tons per day, it is already good enough.
Okay. Okay. So we are still waiting for the question, but if you don't mind, I will ask more question. Maybe most of the participants, they don't maybe they don't understand how this microwave can hit the rocks and then crack present inside the rocks. So maybe can you explain more how this microwave can convert
Yeah, it is basically very similar to the microwave oven in your kitchen. When you supply an electric and magnetic field, I don't have that slide. Anyway, when uh, in your microwave oven in your kitchen, when you supply electric and magnetic field, basically from the molecular point of view, that high intensity electric and magnetic waves disturb the molecular bond of your materials. And then because of the wave, it oscillates, and from the molecular point of view, it creates chaos, and that chaos basically absorb that energy that heats up the materials. And why in rocks it create cracks? Because usually rocks consist of different grain materials with different thermal expansion. And say, in this case, for example, iron ore. So there is a gunk material and the ore, right? It expands because these two materials has different thermophysical and dielectric properties. One grain will expand more than the other.
Okay.
And when the grain expand, it creates a micro cracks. It cracks the bond between these materials. That's why we see a lot of micro cracks inside the rocks and the ores, basically, because of this difference in the thermal expansion and heating rate. And then in the grain boundaries, we see a lot of micro cracks. And that micro cracks basically reduce the strength of the ores. And this is very useful for the processing when you excavate, when you crush, when you grind. This decrease the energy significantly.
So I think the rocks fail because of the thermal stress from the microwave.
Correct. Yes.
Okay. So far you just experiment with this basalt rock, or you have any result for any kind of rock or minerals, for example?
As I mentioned earlier, we have different samples. We have granite, we have kimberlite, we have iron ore, we have gold ores. But some of the ores, we cannot publish it because we are in the non-disclosure agreement with our industry partner. Okay. So what we can present here is basically the common rocks like basalt or granite. But we have some result on the kimberlite, on the iron ore, on the gold ore as well.
Okay. So because I think Professor Agus just has limited times, we have one question from Mrs. Frieda Hariyani, but I don't know, it's but I just read the question. Can this technology predict or make simulation for earth ground shaking like earthquake?
I don't really understand the question.
Yeah, this microwave technology, can this technology predict or simulate the earth ground shaking like earthquake, like megatrust in Java Island, for example?
Well, this frequency of microwave is designed to create molecular chaos inside materials and thus heating the materials. But there might be some different types of waves at different frequency and intensity that might be able, like ground penetrating radar, for example. It uses different types of waves that like it is quite common in ground mapping to map what is inside the ground. So in mining, it is quite common to use ground penetrating radar, for example, to understand the geology of the ores and to look for if there is any ores that can be extracted. So maybe this kind of radar technology with different frequency, different intensity can be used to map uh, the geology of the area that might have some potential for earthquake. I'm not sure, I'm not geologist, but I'm not on the capacity of answering this question, but to my understanding, there are some radar technologies in mining that is commonly used from ground mapping.
Okay. So I think it's very good and interesting presentation, Prof. Agus. So if we don't have any question, I would like to thank you to Professor Agus P. Sasmito, who available to join with us tonight. So I don't know, it's in Montreal, I think it's half past
10:30 a.m.
Ah, 10:30.
Yeah.
So it's not deep in
11 hours behind.
Quebec. So,
okay, thank you, everyone. I really appreciate the invitation and hope you learn one or two things from my presentation.
Yeah, it's I think it's very inspiring presentation, because with the physics, there are many things can be done to solve the problems in the mining, or perhaps in the metallurgical problems. Here in our department, we have a lecturer who used the tomography method to what we call it, to monitor the flow of the fluid, or the reaction in the metallurgical process.
Mm-hmm.
So I think it's very interesting, and I hope the participants, our students, will inspire by this presentation, and using the physical method, the chemical method, or the biological method to solve the metallurgical or the mining problems. So thank you very much, Professor Agus P. Sasmito.
My pleasure.
Please send the slide to us, because if you don't mind, because all the participants will receive the electronic certificate, and also the slides from the speakers.
Okay, sure.
Okay, so thank you very much again, Professor Agus. And for all the participants, we will share the Google form, the presentation. So please fill in the form. In the meanwhile, we will see the presentation of Mrs. Giska. Hello, Mrs. Giska Rahmadita.
Hi.
Oh, so sorry for this unexpected situation.
Yeah, I'm sorry. I got a family emergency situation this morning, so I'm sorry for being late.
I hope everything's fine.
Yeah, I hope so. But yeah, at least I'm here now, and I'm excited to share my project with you all.
Okay, so I will read your curriculum vitae. Is Giska Rahmadita. He graduated from Metallurgy and Materials Engineering for the Bachelor of Engineering in Universitas Indonesia. and then she continue to pursue the master degree, 2 master degree. First in Master of Science, Engineering and Health, Innovative Materials at Institut National de Sciences Appliquées de Lyon di France. And the last one is Master of Engineering in Material Science at Department of Metallurgy and Materials Engineering, University of Indonesia. Now she study at Hoops Lab at Biomedical Engineering, McKelvey School of Engineering, Washington University in St. Louis, and also at the Hoops Lab and Jenin Lab with collaboration research on mechanobiology of engineer heart muscle. She will present about the tissue engineering strategies. It's a biomaterial topics. So please, Mrs. Giska, the screen is yours. You have 45 minutes maximum, and then 15 minutes for the question and answer.
Okay. Thank you. So can you see my slide share?
It's fine, it's fine.
Okay, thanks. So perfect. So thank you, Dr. Aditya, for the opportunity for me to share about my work in Washington University in St. Louis. So basically, in my abstract, it was maybe too general for you to, and might be it can be learned from anywhere. And here I'd like to expand my topic for today. So I can start with my profile and the WashU, because I know that most of the students in Untirta might be not really familiar with WashU or Washington University in St. Louis. And then I can go in general knowledge about tissue engineering and biomaterials development. Then I can go further with my study. It's more specific in elastomer grafted for induced pluripotent stem cells. But it might be new for most of us, but let me know if you have any questions next. And then if Dr. Aditya allowed me, I will also share about like few minutes about scholarship opportunity in my campus. So yeah, Dr. Aditya has introduced me to all of you, and I'm very happy to share my presentation today, because I got also a connection with Cilegon, the beautiful city, when I did my internship in PT Chandra Asri Petrochemical in Cilegon. So a little bit about WashU. WashU is a university in St. Louis, Missouri, in the United States. So here we have 14 universities, and WashU is one of them. And it's established a long time ago. We also got many Nobel Prize winners, and like recently we get Nobel Prize in 2020, like this year, by Charles M. Rice. He got the Nobel Prize winning research while he did his work at WashU. And we are very proud to be a Washington University community in St. Louis, because it is our research university with high funded. And I'm also proud to be McKelvey School of Engineering students. So here we can study about mechanical engineering and material science, but also we can learn from interdisciplinary field. So I'm here working in mechanobiology. So it's like how you learn the effects of giving some mechanical cues, mechanical characteristics to lead any biological consequences to the tissue. So yeah, I can start with the tissue engineering. Tissue engineering is an interdisciplinary field that applies the principles of engineering and the life science toward development of tissue substitutes that restore, maintain, or improve tissue function. So it's basically the field that we as materials engineer or the metallurgical engineer can work with other people from different backgrounds to work in the improvement of tissue function. And it's kind of, yeah, it's kind of obvious for us, like maybe in Indonesia, it's not quite well known at this point about tissue engineering, but based on the Time magazine, it will be a tremendous change in tissue engineering, that tissue engineering will be the 10 hottest jobs and maybe the first hottest jobs in the 21st century. So this is our time to like open our knowledge to this opportunity, so Indonesia can foster our ability, our skills to be able to be a part of this tissue engineering field. So as I mentioned earlier, tissue engineering is kind of a multidisciplinary disciplinary field that can improve our organ function or tissue function. And there are some strategies to be able to apply this tissue engineering. So here we get four elements. We have cells, and our final aim is to improve the organ inside our body. And we also get our biomaterials, and then with some regulating factors, we can incorporate our tissue in vitro. In vitro means outside our body. So the four strategies that I would like to mention is we can incorporate our cells and our biomaterials to grow any tissue in vitro outside our body. And then once we get this regulated biomaterial scaffolds, we can implant to our body. And the second strategy is just to incorporate our cell and our biomaterials to the implantation, to insert to our body. Or we could also just do implantation or incorporation of cells into our body. Or without any incorporation of cells, we can also apply the biomaterials directly to the body. So here we can see that biomaterials has an essential role in this tissue engineering field. So I can continue with some biomaterials development. Yeah, in Indonesia, we get ambiguity of definition of biomaterials, right? So some of people can say biomaterials as like bio-based materials, the ones that synthesized from natural fiber, like from ijuk, or from bamboo, or from starch to make polylactic acid. So it's bio-based materials. But here, what I'm gonna show you about biomaterials in this aspect is materials that are used to directly supplement or replace or study the functions of living system. So it's the aim of the biomaterials is to be incorporated with cells or with organs and tissue. So it is intended to come in contact with the living tissue. So we need some aspects to be considered more attention, like the biocompatibility, how the cells can interact with our materials. And it's also can be used in any substance, like for drug delivery, like all of the possible ways to improve organ function. So here it's very important to also consider some medical interaction, like medical application. So we work with some other people from medicine or from biomedical engineering. A little bit about the history of the biomaterials. It's actually already applied so long time ago, when like in ancient times, while they use artificial biomaterials to make boring teeth. So they use gold or silver or wood to support the structure of teeth. And started in early 1900 or 1900, bone plates were successfully implanted to stabilize bone fractures and to accelerate the healing of the bone fractures. While by the time of the 1950s or 60s, blood vessels replacement were in clinical trials, and we also get some artificial heart valve and hip joints. And yeah, as you know, like what these biomaterials has to do with us as metallurgy or materials engineers. So my background is mostly about materials engineering. So we know, like I'm pretty sure all of the students and all of people here know about the 4 groups of materials. We get polymers, ceramics, metals, and also composites, right? So polymers can be used for drug delivery device, skin cartilage, or ocular implants, and ceramics can be used for some hard tissue support or scaffold for bone replacement, dental implants, and also metals also can be used for hard tissue scaffolds. Like there are a lot of opportunity to develop biomaterials throughout our body, from the head, eyes to the tools. So I'd like also present like the evolution of biomaterials. There are 3 generations of biomaterials. Like the first generation was largely dependent on being inert. So in first generation of biomaterials, we don't want any interactions between cells and our materials implanted to our body. So it's mostly used for teeth or for dental functions, while metals is the king in this first generation of biomaterials. So we can see some, or like in ancient period, we see like gold and silver implanted to our teeth to support the function and the structure. And the second generation of biomaterials concern more about the interaction between cells and materials. So we don't want it to be toxic. but we need some some adjustment between cells and materials, like some interactions. So here, people already start to collaborate between physicians and engineers, because physicians know like what living systems look like, what are their mechanism, and the engineers on the other hand knows about the materials, how is their mechanism in different pH, different temperature, different fluids, and so. So here they collaborate and use advances in materials science. While in the third generation of biomaterials, development has focused on bioactive materials. So it's like if you have some damage in your tissue, the cells will be interacting with your materials, and also here we will get some degradation of our materials, which induce the cells to do self-healing, like they regenerate themselves. So in the end, we get our native tissue, which is naturally from our body. And most of them are polymeric devices. So these are the examples of biomaterials in tissue engineering. So as a soft tissue, I can show you the skin tissue engineering. Well, we can use dermagraft. This is basically PGLA, like polyglycolic acid and polylactic acid. And we can see like in 2 months, like we get total reparation of skin tissue, which is actually this final tissue is not the one that we synthesize, but it is our cells that being generated, like induced by the incorporation of our biomaterials. Okay, and we also get the hard tissue replacement, like bone scaffolds. So if we can look at the bone, we got like 60% of epithet, which is calcium phosphate, and 30% of organic phases. It can be collagen and other extracellular matrix. So we need to make bone scaffolds which mimics the structure of the bones. You know, like our bones have porous structure, so we can engineer the materials to be mechanically supportive as a bone, and also have this porous structure so the cells can adhere or can attach to the scaffold, and then it can grow and regenerate themselves. So here we can see beautiful porous structure, which is all of the porous and the structure are interconnected. And we can do this in Indonesia, where we need only like freeze drying and some chemical process. Okay, so I've already talked about the evolution of biomaterials from first, second, and third generation. And here, like in this era, people are doing more focus on the functional tissue engineering construct. And this is what we did, what we are doing in our lab in Washington University in St. Louis, especially in the HIPSH lab, the place that I'm working on. We work on how to mimic the key aspects of tissue microenvironments for in vitro modeling, like outside the body, to support the tissue engineering or regenerative medicine. So regenerative medicine is part of tissue engineering, which induce the self-healing of the cells, or also like we solve the whole problem by inducing the by inducing the functional of the cells. So I'm working on two projects. The first one, genetically defined engineered tissue for pharmacogenomics biological testing, and also new materials for local presentations of biologic from cell polymers. But today I'm gonna focus on this one, like genetically defined human iPSC. So this study is basically motivated by a high number of cardiovascular disease worldwide. So it's now still the first killer, like, and especially sudden death. One of the cardiovascular diseases is hypertrophic cardiomyopathy, while you have thickened wall of your heart, thickened septum, and thickened left ventricular wall. And as the consequence of this thickened heart wall, the heart is not really able to pump your blood throughout the body. So here, many animal studies has been conducted to study about this mechanism, and it includes the animal study. But if you can see here, these are like human action potential, like the mechanism of your heart beating in every single beat. We have different mechanism between human and mice at least. So instead of only rely on the animal studies, we need an in vitro studies, like a testing outside our body or a development outside of our body with human genetics. So we need to know how the physiology of the heart needs to be translated into this in vitro system. Okay, so as I firstly say that we need in vitro system with human genetics. How we can incorporate the human genetics? Like here, we have stem cells. So yeah, stem cells is basically the cells that have the ability to divide, like to grow, reproduce themselves in culture and give rise to be specialized cells. Like stem cells is a baby cells that don't have any identification. Like we have some skin cells, some cardiomyocytes in heart cells, but stem cells is just baby cells without any differentiation. So what is cellular differentiation? That is the process that less specialized cell, like the stem cells, becomes a more specialized cell types. So from stem cells, like the baby cells, we need differentiation mechanism to be able to produce the cells that we want. In this case, we need the cardiac cells, or we call it cardiomyocytes. And this cardiomyocytes is defined from human-induced pluripotent stem cells, like the stem cells that I mentioned earlier. And by doing tissue differentiation, like it's maybe more biology for this aspect, because it's basically we make the stem cells into the cardiomyocytes. We call it differentiation process. So here, after the differentiation, we can see the beating cells here. Like it's literally beating, as you can see from your heart. And we incorporate this in vitro human-induced pluripotent stem cells to study about some cardiovascular disease. But the second aspect here, we need to know how the physiology of the heart needs to be translated in vitro system. So if we see how our heart beats, it's basically related to the preload when the heart stretch at the maximum to be filled with the blood, and the afterload mechanism. Well, it's basically the heart contracts, and the tension that the heart muscle has to overcome is afterload to be able to eject the blood throughout the body. And here we know that mechanical cues, like mechanical aspects, can affect heart muscle contraction. So other people, like other researchers, try to incorporate the human pluripotent stem cells cardiomyocytes with type 1 collagen as the extracellular matrix, and also incorporate with fibroblasts. And we make this, and they made this shape and then stretch it to be able to see how the preload, like the stretch of the heart, can affect the biological function. And related to the afterload, like when you stretch, when the heart contracts, so other people also did some study on the stiffness. So these are the cells, and these are the PDMS substrate with a beam cantilever facing upward. So it's like if you have cells between these pillars, it will contract and the cantilever will be bent. So here we can see if we make stiffer substrate here, we can see higher contraction expressed by the cells, by the cardiac cells. But here the issue is hard to do this hard to do this experiment in large scale due to complexity issue. Like if you incorporate collagen, so you have other factors that might play a role. So you don't know which one to focus on. So here in the HIPS lab in WashU, we derived we made iPSC engineered heart muscle. It's basically you have these stencils like this mold. Yeah, I know that in metallurgy you have been working with mold and some other stuff for you to cast your melted iron or melted metals. And here it's basically similar. You have the mold and you can pour your cells into this mold, and by several days you can see incorporation of the cells inside these stencils, and it can do traction force and matrix remodeling between the cells, and you can see these highly aligned cells within this area. You can see from the electron micrograph picture, this is the cells. And here in the middle of the tissue, we can see a highly aligned cells, which is called sarcomere. And it's specialized in myocytes, like in myocytes. And it's also important for us to see about this structure because it can be related to the heart function or to the heart function or electrophysiology. So it's amazing to see how these cells is beating. And this is what we study further in this paper. So here we have cardiomyocytes inside the stem cells, inside the dopant stem cell. The material that we use as the substrate is PDMS. It's basically polydimethyl siloxane or silicon. It's a kind of elastomer that can be cross-linked or it can be cross-linked under radical polymerization mechanism. So we can, by incorporating the base and the curing agent, this curing agent will induce the polymerization of the polydimethyl siloxane. And this is elastomer. And why we make PDMS? Because like with polymers, you can do some surface modification. It's pretty easy to make any modification in the atomic or molecular aspects. So here what we did is we have the PDMS, and by doing some plasma oxidation, we have like this OH group on the surface of the PDMS, and this hydroxyl group would be able to would enable us to modify some chemical treatment. Here we have silent treatment. So it's basically, we have this silicon oxide and a long branch of polymers, which ended by the NH2 or the amine group. And then by doing some other cross linkage by glutyraldehyde, this PDMS with NH2 group can be covalently bonded with fibronectin. So what is fibronectin? Fibronectin is basically a protein that can bind into your cells. So once we get the fibronectin into the PDMS, the cells can attach to our PDMS. So then we can mechanically couple the cells with our PDMS substrate. Okay, and then we have our stem cells on top of the substrate as well. And I also did some finite element analysis to see how this, how the traction force can be expressed in this tissue. And maybe I would not go so into details, but yeah, basically we got our tissue inside this mold, and we were interested to see this sarcomere formation, or like this tissue formation here. And then by observing this beating contraction, we convert it to the fluorescence signal. So we know that the high traction is observed within this knob area. Yeah, I wouldn't go further with this FEA analysis, but yeah, maybe it's basically we have the high stress observed within the knob area of the PDMS substrate. And then what we can see here, by modifying the stiffness of the substrate, like under the tissue, we have the PDMS substrate, and we modify the stiffness of the tissue to see differences in traction force and sarcomere and the bit rate. So what we can see here from this graph, in day 16, we get a higher average of bit rate in day 16, and also from the traction force in day 1, we get higher traction force by having higher stiffness of the PDMS substrate, and it's also expressed in day 9 after the tissue incorporation. Then we can also see here that in 30 kPa we have more uniform or more aligned structure of the sarcomere, while this one is pretty random in direction. But in 30 kPa, it's more more uniaxially aligned, which is good because in our heart, it's basically all of the structure of the cardiomyocytes is very in line or highly aligned. So here we can see the sarcomere organization structure is quantitatively more aligned, but it doesn't give any effects to the sarcomere length. And then the conclusion from this study is we developed a new in vitro platform to study how the mechanical aspects affects the micro heart muscle physiology, like by doing several levels of rigidity, we investigate the micro heart muscle behavior, and these cardiomyocytes iPSC have better cell alignment and sarcomere organization, and it's open some other opportunities to study about the cardiovascular disease. Okay, and I need maybe 3 to 5 minutes to show about the scholarship opportunity, because I know that it might be helpful for the students or the alumni of Metallurgy Untirta. This is my scholarship that I pursue right now. It's McDonald International Scholars Academy. It's basically the scholarship that will develop a cohort of future leaders. Because here in WashU, we have several partnership with other universities worldwide. So if you have some good students with a good leadership, global mindset, and also have some eagerness to contribute to the community, I will be happy to answer any questions about this scholarship. And it's very good scholarship because they provide a long-term programming, a long-term training or workshop like leadership training and so on. And then, it's provide full tuition scholarship and monthly living stipend, and 5 years if you finish your PhD. And you can also get annual travel allowance, so you can go back and forth to Indonesia every 1 year. Yeah, and also cultural and leadership training. So it opens the chance to go to Washington DC or to the New York to study about some politics and other stuff as well. So it's like a very good opportunity for you guys to join this prestigious scholarship. And you will also, of course, you will get a mentors and global network of students and alumni. Yep. So, yeah, that is all. And I would like to thank you for Dr. Aditya for the opportunity today. This work is a summary of what I did during 6 years of being a researcher and lecturer in Universitas Indonesia. So I've been working with some undergraduate students, like they are very eager and very potential to be a researcher. And thank you for my groups in the WashU community as well.
Okay, thank you, Mrs. Giska. We have a question from Mrs. Frieda. Assalamualaikum, Mrs. Giska. Engineering really is interesting for Indonesian researchers. Riza Putranto, and also alumni of French scholar. shared in Instagram that his research in genome structure, especially COVID-19, that this virus is still doing silent mutation. Is there any possibilities in tissue engineering, especially stem cell, to overcome effect after infected like lungs recovery?
Yeah. So yeah, this is interesting question. So it as I've read, it might be more about the treatment of the COVID-19, how the stem cells can cure this disease and prevent some complications. So yeah, this is interesting, but you know, like in stem cells, because it's undifferentiated cells, we couldn't just apply it to our body because it can be other cells, and if it can, I mean, like if it grows so fast, it can also be a potential to be cancer cells, right? Because we don't know how they grow, and we also don't know how the effects of COVID-19, if it's can induce some side effects. So I guess, but this is a good potential for stem cells to be answering the COVID-19 system. In our lab, we are also working in some COVID-19 projects on doing some drug testing. So, but it's not related to the lung, but more about the cardiac tissue, about the heart tissue, how the side effects of the COVID-19 drugs can affect our heart function. But yeah, it's an interesting question that needs to be answered further by doing some more specific research. Thank you, Dr. Frieda.
Okay. The other question is from Mr. Lukman Besar, Zwickrol PT Ltd. For adequate modeling, the biomechanical behavior and the underlying microstructure of soft biological tissues must first be accurately determined. As most of the tissues in the body are subjected to multi-axial loads, what kind of testing application in your research to determine the mechanical characterization of soft biological and artificial materials?
Yeah, this is a good question, because yeah, here like biomaterials cannot stand by themselves. We need also to study about other biomechanical and mechanical characteristics. So here, what the test that we applied to this study is basically we test the materials mechanical properties by doing compression test. So we know that our substrate is 5 kPa or 15 kPa or 30 kPa. But for the cells here, what we did is by doing, what we did here is by traction force microscopy. Let me show you. It should be here. Yep. So by showing the beating of the cells, we can see the contraction of the cells during a certain period of time. And what we did is by tracking with fluorescence, like we do traction force microscopy observation, and this contraction, like this fluorescence expression showing the contraction of the cells, and then we know this different traction force observed from our cells. So it's basically in micronewton, which corresponds to the stiffness or the traction force of the tissue.
Okay.
Mhm.
Do we have any question from the participants? So for the participants, please complete the Google form of your presentation in this online seminar. You can find it on the chat room. So maybe we will wait just 1 or 2 minutes if
Yeah.
you still have any question.
And
So
mhm.
Mrs. Giska,
Yep.
how do you load this substrate?
Mhm.
You what have you done with the substrate?
The mechanical testing.
Yeah, have you stretched the substrate before use for the experiment or?
Oh, yeah, that's an interesting question. We are planning, like in the further study, we are planning to really stretch so we can see the preload. But in this case, it's basically we just modify the stiffness of the substrate. And then by modifying the stiffness of the substrates, we can see the stiffness of, like, we can correlate with the stiffness of the heart. So if it's highly stiff, you wouldn't be able to contract or to eject the blood. This is what we want to imply by uh, uh, modifying the stiffness of the substrate.
Okay, so you just control the stiffness of the substrate of the PDMS.
Mhm.
You play with the crosslink percentage, I think.
Yeah, and also the crosslink, we 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 incorporate some silicon, so we just make different ratio of the PDMS that we use.
Okay, okay. So what I understand is you modify the toughness of the PDMS substrate,
Mm-hmm.
and you see this toughness difference affect this IPSC micro heart muscle.
Yeah, that's perfect. So basically we modify the stiffness and then we study the physiology of the cardiomyocytes in these cells by doing some traction force microscope to and some micrograph picture to see the formation of the sarcomere cardiomyocytes.
I don't understand. I never use this traction force microscopy. Can you explain to us what is traction
Yeah,
force microscopy?
sure. It's basically you can, like, we have these cells, like we have this tissue and you put it into the microscope, and then by having this bead, we also incorporate some like fluorescent beads into the substrate. So this fluorescence will be brighter if you have higher traction force. Like if you have higher traction. So here what we can see from the heat map here, like different colors showing different level of the traction of the cells. By the red area, so you have higher traction force inside this region compared to the blue region. And this is how we can see the quantitative data of the traction cells that we can observe from this curve, from this bar chart.
Okay. So I will check if we still have any question. Actually, it's an interesting topic. I also I have worked with degradable biomaterial, metallic biodegradable material in Quebec, Canada. So, but maybe most of the participants maybe they don't familiar with these biomaterials things. But
Yeah.
it's a very nice presentation, and thank you, Mrs. Giska, for the presentation.
Thank you so much. And I really like to be here and to see some excited students still being here until late night.
Yeah, and we are sorry for this for the late, but it's okay. So once again, thank you for Mrs. Giska, to Mr. Chayo, and also Professor Agus Sasmito for their kindness to present some interesting topics from yeah, for example, Mr. Chayo, it's really benefit for engineer, for metallurgical engineer, for example, who can use experiments and simulation tools to predict or to modify the structure and the properties of the metal, for example. And then the next presentation from Professor Agus Pesasmito, I think it opened our mind that we can use physics or chemical or biology, science and engineering to solve the problems in metallurgy field, for example. So it's maybe it's very simple. You use microwave frequency to hit the rocks, so it creates a micro cracks inside or on the surface of the rock, and it will help to crush the rock with lower energy, for example. And the last presentation from Mrs. Giska at Washington University, it's a challenging topic. It's very interesting, and many people now do research in biomaterial, and also we have a course in biomaterial here in our department, and I hope our students can see this online seminar and can get the similar scholarship that Mrs. Kiska got at the Washington University at St. Louis. So on behalf of the committee, I would like to thank you to the three speakers and also all the participants. We are sorry for the late of the online seminar, and please fill the Google form for your present. We will send by email the e-certificate and also the PowerPoint from the three speakers. So thank you very much and good night. Bye. We give sorry, we will give you more or less 5 minutes to fill the Google form before we end this Zoom meeting. Thank you.